Hi, my name is Saeed Paliwal, and I'll be presenting our paper, Directed Graph Embeddings in Pseudo-Riemannian Manifolds, accepted to ICML 2021. This work was done together with my colleagues Aaron Sim, Maciek Wiatrek, Angus Brain, and Paddy Creed. The problem we're hoping to tackle in this paper is the graph embedding problem. Graphs are ubiquitous data structures, found in everything from smaller social media networks to biological graphs to large heterogeneous knowledge graphs with millions of nodes, using data integrated from several sources. In order to learn and infer on graphs, we'd like to find a vector representation of nodes in the graph, as shown on the right. In this work, we present a new approach to graph embeddings beyond the standard Euclidean and Riemannian embedding methods traditionally used to embed graphs. Our approach, Pseudo-Riemannian embeddings, represents graphs and manifolds that allow for greater flexibility in representing key structural features of graphs that Riemannian embeddings struggle to represent. Particularly, there are three key elements of graph representations that we address. The first is the difficulty traditional methods face when representing nodes that are semantically similar but disconnected. Consider A and B. A and B are two nodes that are semantically similar in that they have a large overlapping neighborhood set. But having this neighborhood overlap doesn't necessarily imply that A and B are directly connected. This happens a lot in real-world graphs in everything from social networks to competitive sports to scientific collaborations to biological graphs like gene regulatory networks. In standard Riemannian embeddings, the problem we encounter is that Riemannian manifolds cannot disambiguate semantic similarity or overlapping neighborhood sets with edges in the graph, or a direct connection between nodes A and B. Shown here is a toy example, in which we have a tripartite graph in which there is no connection between the two blue nodes. If we embed this graph in Euclidean space, the likelihood model we use is the standard Fermi-Dirac distribution, shown here in simplified form. This gives us the probability that any two nodes are connected, and is the function of s squared, or the squared distance between the nodes. As we can see using Euclidean embeddings, an edge between the two blue nodes has a probability of 0.5, despite them being unconnected. Let's try embedding this graph in Minkowski spacetime, a simple flat pseudo-Riemannian manifold with one time coordinate. The probability of an edge existing is still a function of the squared distance, but because this is a pseudo-Riemannian manifold, we're allowed to have negative squared distances. We also have the preferred direction of time, which allows the model to flexibly keep two nodes space-like separated, maintaining the lack of edge between these nodes, while constructing causal light cones from these edges to their overlapping predecessors and successors. Because of this, the probability of our nodes being connected drops to 0.01 versus 0.5 in Euclidean space. Another problem we encounter in Riemannian embeddings is the restrictive assumption of transitivity. What this means is that if node A is connected to node B, and node B is connected to node C, then there's a high probability that node A is connected to node C. What if, actually, the graph is just a simple chain, and no link exists between node A and C? In this work, we extend the standard Fermi-Dirac probability function to address this issue. Starting with the standard Fermi-Dirac probability shown on the left, we see in red the regions of high probability and in blue the regions of low probability, with one of the nodes being at the origin. The first problem of this probability landscape is that it's symmetric in time, which is an issue if we want to encode directed graphs, because directionality is not implicit in this landscape. The second problem is that because of the probability distribution in the future light cone, if you have a graph like the one in the previous slide, if B follows A and C follows B, by a function of C being further in the future of A, it has a higher probability of being connected to A, and embedding a simple chain is impossible. Here we propose the triple Fermi-Dirac likelihood function, which is a product of three of these Fermi-Dirac terms, with a geometric mean taken in the end. The two terms we introduce are Fermi-Dirac distributions, with the square distance term being replaced by a time coordinate shown in blue, one pointing to the past and one pointing to the future. The first term allows us to maintain the light cone structure, and importantly, this function is not symmetric in time and is only likely in the future. Additionally, the parameter alpha allows us to flexibly decay the probability into the future, which allows us to break the assumption of transitivity and encode graphs like a simple chain. To show the model's ability to represent graphs with varying transitivity by tuning this parameter alpha in the loss function, we model a simple 10-node chain. No transitivity shown with the green arrows in plot A, and full transitivity shown with the orange arrows in plot A. Alpha, as we saw earlier, varies the probability decay in the time direction, where the larger the alpha, the stronger the decay. Using two values of alpha, 0.001 and 0.075, we see that the smaller values of alpha are more able to capture full transitivity, shown in plot C, whereas smaller alpha on a simple chain in plot B ends up assigning a higher probability to negative edges or transitive edges that do not exist. The third problem we're hoping to address is the problem that most graph embedding methods struggle to represent directed cycles. We address this issue by introducing a compact time coordinate to encode graph cycles. Here we consider a cylindrical Minkowski spacetime, in which space is literally wrapped around the time coordinate, and an anti-de Sitter spacetime, which has a natural S1 times Rn topology. To demonstrate the ability of our wrapped geometries to model graph cycles, we then embed a simple 5-node loop, shown in plot A, in flat Minkowski space, and curved cylindrical Minkowski and anti-de Sitter spaces. In all three manifolds, we are able to recover the true node ordering. However, the Minkowski manifold, as a function of being two-dimensional, is unable to correctly encode the positive edge from node 1 to 2 that travels seemingly backwards in time. The full cycle, however, is more easily captured in wrapped cylindrical Minkowski and anti-de Sitter spacetimes, which allow all edges to have high probabilities. Shown under each plot is the negative log likelihood of the model, which again shows us that cylindrical Minkowski and ADF spaces outperform Minkowski. For reference, all three Pseudo-Riemannian manifolds outperform Euclidean manifolds with a negative log likelihood of 17.24. While we've shown the ability of Pseudo-Riemannian embeddings to address key issues in certain toy examples, we'll now compare our method to competing methods on standard datasets. What we find is that Pseudo-Riemannian embeddings outperform Euclidean and Hyperboloid embeddings on the DREAM5 dataset. The DREAM5 dataset is a gold standard set of edges from a genome-scale network inference challenge. This particular dataset of the DREAM5 set is a synthetic gene regulatory network. Here we compare Pseudo-Riemannian embeddings with standard Euclidean and Hyperboloid embeddings, but also compare flat Minkowski space with wrapped cylindrical and anti-de Sitter spaces. Interestingly, we see that cylindrical Minkowski outperforms all the Pseudo-Riemannian manifolds as well. To highlight our method's flexibility in modeling transitivity, we test our method on the WordNet dataset, a stable dataset in directed acyclic graph inference. Here we show how the performance of our method on WordNet with varying degrees of transitive closure perform against a set of competitive methods. We split these models into flat space embeddings, shown in the top half of the table, and curved space embeddings, shown in the bottom half. Encouragingly, our method outperforms all flat space embeddings, as well as most curved space embeddings, and is competitive with hyperbolic and spherical approaches, which are similarly suited to represent the hierarchical structure of WordNet. Finally, we perform an ablation study to examine the relative contributions of 1. The Pseudo-Riemannian geometry as reflected in the presence of the negative squared distances, 2. The global cylindrical topology, and 3. The triple Fermi-Dirac versus the Fermi-Dirac likelihood model. We run the model on the duplication divergence dataset, which is a synthetic protein-protein interaction network. The dataset is a directed graph with cycles. The results are presented here, and we see that all three components combine to produce a superior performance of the anti-de Sitter and cylindrical Minkowski manifold embeddings, with the S1 cylindrical topology arguably being the biggest contributor. What's important to note here is with the addition of each additional feature, we increase performance positively. In conclusion, the main takeaways are that Pseudo-Riemannian embeddings allow for flexible representations of unique graph structures, such as semantic similarity, directed cycles, and partial transitivity. Our method outperforms competing manifolds on synthetic PPI networks and the in silico DREAM5 network on the task of link prediction. And 3, this embedding method achieves state-of-the-art performance on link prediction using the WordNet dataset. In the future, we'd like to extend this model to include multiple relations, and possibly use Pseudo-Riemannian embeddings for network inference, not just inferring missing edges in a graph, but inferring a graph from continuous data. Thank you so much for listening. I encourage everyone to take a look at the paper, and please let us know if you have any questions.